So we're getting to the fun stuff here. Now, like I said, what we're doing today is not on the final exam, it's just for your enjoyment. And I mean, it's kind of like why you take a differential geometry class, right? Is to learn cool applications. There is no cooler application than general relativity, right? And so general relativity is all about curvature of space-time and all that. And so the curves and surfaces in R3 that you're responsible for the final exam, that's fun and everything, right? And actually has plenty of material for a course. But how does this generalize to higher dimensions? That's what we're talking about in this last part of the course. And so we'll still draw a picture of some surface inside of R3, but now we'll think of it as an n-dimensional surface, and it's not inside anything. Okay? And we're trying to figure out how do we do geometry when it's not inside anything. And so, well, we'll still do the same thing. We'll have a UV coordinate chart, right? Remember before we had a UV coordinate chart? And then you have a map X that maps that into your surface. But now this is not a UV. At best it could be a U1, U2, and so forth, but it's more traditional to use X1, X2. So we'll have, instead of U and V, we'll have X1, X, and of course it'll be a cube, right? And so we can have X1, X2, and then X3 at the dot all the way up to Xn, right? Well, how do you have an Rn coordinate chart, right? Some cube, higher dimensional cube. And it'll map over here. And, instead of calling it X of U comma V, because remember that's where we have X, Y, and Z here. I don't know. I mean, we could call it anything. Let's call it phi, right? We're not going to be talking about it too much. Because really the thing that was important, if you remember, was the XU and XV over here, right? That's what we really need to know. What are the vectors over here? And those are simply the images of the ij's and k's. In other words, you look at the unit vectors over here, right? Now what's a unit vector over here would be like ddx1. And by the way, we're supposed to use superscripts here, sorry. And that's Einstein notation. So ddx1 and then dx2. These are the, and so on, these are the unit vectors like the ij and k over here. And up to ddxn, right? And when you look at the images of them over here, then you get these vectors over here, which are not necessarily perpendicular. It's like the xu and the xv. And really, we have to decide what to call them. And so why don't we just call them the same thing we call them over here? Okay. And so this is sort of, because if we just say, and when we write dk, right, what we mean is dxk. And by the way, just a quick note on Einstein summation notation and all that. That's an upper index for the x, but because it's below the fraction sign, it counts as a lower index as for the whole object, and so you write as a lower index over here. Okay, that's just a convention that makes everything work out. Okay. All right, so instead of xu and xv, we're going to have these partial derivatives, which by the way still makes sense because we have these coordinates x1, x2, and x3 over here, or up to xn, and it's just saying it's in the direction where you increase one coordinate but hold the other coordinates fixed. Okay, so you think of it as ddx theta or ddx phi if you're in spherical coordinates on the sphere, latitude and longitude. Okay, so everything makes sense so far? Okay, it's just notation, and notation is like half of differential geometry. Especially when you're getting started, it's really annoying. Okay, so if you're like, I think I understand everything, but this is the notation, right? That's normal. Okay, now what we need is, it turns out this is what Gauss realized, is everything is about the metric. Okay? And so what we need is, how do we take a dot product of xu and xv? Now we called xu dot xu is what we call E, right? Xu dot xv was F, and then xv dot xv is what we call G, right? And so instead of E, F, and G, what we're going to do is we're going to use G11, G12, and G22. And so in general, we'll say Gij is equal to the dot product of the partial derivative, partial I, partial j. And sometimes we'll write it as G of partial I comma partial j. But the point is, this is sort of like your E, F, and G's here. Okay? And it's the metric, and think of this as given. Now, so this is, it's arbitrary. In other words, you kind of get to choose it, okay? Like, the point is the same way that I could just make up any F and G I wanted and say, what's the Gauss curvature? You plug it into the formula and you compute the curvature, right? So when we say, like, how do we define this metric, really it's the GIJs that define the shape of the object we're talking about. Now there's also the topology of this thing. It has to do with how the coordinate charts overlap and blah, 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 right? But let's not focus on that. That's for another day, it's topology, right? That works out exactly the same as before. Okay? But what's new is that we get to just choose the F and G. See, like before you were always computing the E, F, and G's, right? It was sitting inside of R3, and you would compute the vectors XU and XV. You start taking dot products, you would compute the E, F, and G's. Now we're just going to let our E, F, G's be whatever we want. Do you guys get the difference? We're not going to assume it's sitting inside of an R3 or an Rn even. So now you get to choose the metric to be whatever you want. Okay? All right. Now, there was also something called the connection. And that is, if I take the covariant derivative of one vector field, I'm going to start using x, y, and z's as vector fields, okay? So I'll put a vector over these just to emphasize that. Take the covariant derivative of one vector field in the direction of another vector field, and you get another vector field out. Okay? Now, how did we do that before? Before, you thought of x and y as these three-dimensional. We had a two-dimensional surface in R3. You thought of them as three-dimensional vector fields with three coordinates, right? Z would have coordinates, z1, z2, and z3. Or say y would have coordinates y1, y2, and y3, and you just take the directional derivative of each of the coordinates y1, y2, and y3 in the direction of this vector field, right? But the problem is that doesn't make any sense now, because there is no R3. And this is what we did last time, and if you all missed it, it was pretty awesome.
Yep.
All right, it was kind of miraculous, all right? And we came up with a formula for what this is, okay? And this is defined by the Causual formula. Rather than me trying to write it down, I don't actually have it memorized. You can Google it if you're wondering. What was the Causual formula again? Just Google it. You'll get some crazy formula, right? Now, what was the Causual formula based on? It was based on two properties. One is that we want metric compatibility. So if we take the directional derivative of the dot product of two vector fields, x and y, then we still want the product rule to be true. We want, so you notice how I'm using these angle brackets here for the dot product? Again, the dot product is arbitrary. Once I define it on a set of basis vectors, that defines it for all vectors. So typically, you would say what the GIJs are in some coordinate chart, and that would define the metric. And then if I, so now we're going to take this angle thing as known, right? Normally, you would just compute the vectors in R3 and take the usual dot product. Now we got some GIJs that are kind of arbitrary. They choose anything you want. And so what you get then is that we want our product rule still to be true. So whatever this metric is, we want our product rule to be true. Is that the product rule? I think so. So the directional derivative. So okay, let's go over this. Actually, I always found this to be confusing. Just understanding what things are. X, Y, and Z are vector fields. Okay? A vector field dot product of another vector field is a number at each point. A number at each point is known as a function. So this right here is a function. You can take directional derivatives of functions in the directions of other vector fields, can't you? Okay, so, and this gives you a function out. Okay? That's a vector field. That's a vector field. We're taking the covariant derivative. What does covariant mean? It doesn't mean anything. It's just a word. Really, literally. That's what they call it. It's a definition. Or why do you call it a Mazda? Right? It's just a word, okay? take it's like a coordinate derivative is like a directional derivative, but for a vector field, right? You're taking the derivative of the vector field x in the direction of z. That gives me a vector field out. It gives me a vector at every point, otherwise known as a vector field. You take the dot product of this vector field with that vector field, that's a number at each point, otherwise known as a function, plus another function, gives you a function. Okay? And that's just the product rule. This is true for vector fields in R3. So we're like, you know what, it'd be kind of nice if it's true for the dot product in vector fields in R3, wouldn't it be nice if for our arbitrary dot product, whatever GIJs we define, wouldn't it be nice if that's still true? Right, so we can do calculus and stuff. Right? Yeah, that would be nice. And then the second property we insisted on was that if you look at the Lie bracket of two vector fields. By the way, notation is so annoying. You see how I use the square bracket here, but there's no comma. Y'all see that? It's just the z applied. It's really, I could have used anything. Maybe I should have used another symbol, okay? In fact, let me just do that. Just to point out, this is not the Lie bracket up here, okay? This is just z applied to that, okay? Vector fields are first order operators, right? They're directional derivatives. That's how we think of them. And you give them a function, you take the directional derivative. When you have these brackets here with a comma in the middle, that's called the Lie bracket. And that gives you a vector field out. And now, by the way, what was that vector field? Just to remind you that, and I'll erase it here in a second, the Lie bracket, we'll say that the Lie bracket of two vector fields x and y is equal to the vector field z means that if you look at, these are not Lie brackets on here, these are directional derivatives. You guys see what I did here? I have a function f. You take its directional derivative in the direction of y. That gives you a number at each point, otherwise known as a function. And then you take the directional derivative of that function in the direction of the vector field x. That gives you a function out as well. So it's sort of like a second derivative of f in the direction of two vector fields. But then you might say, hey, does it matter which order I do the vector fields? The answer is generally yes. And so if you look at this and look at the difference, you have sort of a second derivative of f minus a second derivative of f. Now exercise, I'm not assigning you all this homework, but if you wanted to, if you're like going to go to graduate school in math and do differential geometry, prove that this is actually a first order operator. In other words, the second order terms all cancel. Okay, so I think that's plausible actually. But it turns out this is actually all the second derivatives of f cancel. All you have left are first derivatives of f. But wait a second, first derivatives of f, those are all directional derivatives. They're in one-to-one correspondence with a directional derivative for some vector field z. And so if that's always true for all f, then that's what we say the Lie bracket is. Okay? If the commutator, right, of x and y as first order operators is equal to the vector field z for all possible functions f, then obviously makes sense to define this as something, right? Now, by the way, this is a multivariable calculus fact. There's no reason why you couldn't have learned this in 211, in 212 or 219 or 222. It's a multivariable calculus fact. Go ahead and play around with it. Take any two vector fields you like, mess around with it, and you'll see that there's always going to be some vector field z that equals that. Yes?
What would be like what kind of vector fields would have a zero Lie bracket?
Turns out there's a theorem that says that if the Lie bracket of x and y is 0, that means they're coordinate vector fields for some choice of coordinates. So for example, if I just let x be 1, 0, 0, let's do this in R3, right? And y equals 0, 1, 0, which by the way, this is just partial 1 and this is partial 2, right? Or I and j or whatever, right?
Yeah.
Then the point is that x of y of f, well, we take the y derivative, that's just taking the second partial derivative, right? And so this is just f, if we think of them as, it's f1, 2, or fxy, right? It's the partial derivative.
That is clearly commute.
And that clearly commutes in this case, right?
Yeah.
And the point is these are equal because partial derivatives commute.
Yeah.
Okay? Now that's a very special case that we have very special simple vector fields, right? If instead x and y actually were functions of position, right? Function of x, y, and z, or x1, x2, and x3, then they wouldn't necessarily be equal.
Yeah.
But the second order parts are, and this is what you want to do, just do examples, play around with it, and it turns out that you can always, the theorem would be that if two vector fields have zero Lie bracket everywhere, then there's some choice of coordinates where in fact they are in fact coordinates like this.
Okay.
Yeah, that's the theorem.
Okay, yeah, so like, if you set them up so that they were like
Yeah.
d theta and d all.
Yeah, up to, because I could also change variables, right?
Yeah,
You do polar
So
coordinates would be the same thing, right?
Polar coordinates would like look in Cartesian coordinates.
Exactly.
Like spatial dependence.
Exactly, but you'd have something different, yeah. So Lie bracket is obviously fundamental, right? And just do examples. If you want to get good at Lie bracket, do examples. That's how you do that. Just compute a bunch of Lie brackets. Okay, so the point is this is a vector field, and it turns out the reason they never tell you about this in Math 212 or 219 or 222 is because this always equals a more familiar formula. It equals this. And so, I mean, why do we need to talk about this when we could just, I mean, just by computation, you always get that anyway. And so it's something you never really thought about. But there's a reason why it's important to us now, is because this still makes sense to the ant. You know, the mathematician ant living on the surface, that's intrinsic geometry. Why? Because the Lie bracket is just talking about directional derivatives, right? It's just directional derivatives. This actually makes sense to the ant. Right? So you don't need the third dimension, right? And so, whereas in multivariable calculus, whenever you use this connection symbol, this derivative of one vector field and another vector field, you're always using the third dimension, right? But these are two properties that we always had in multivariable calculus, and we want to keep both of them. And the ant understands what this means, because that's just the metric, it's just taking dot products, they understand that. They understand directional derivatives, they understand the Lie bracket. What they don't understand is what these upside down triangles are. In the way we do, right? But it turns out the theorem we proved last time is there's exactly one way of defining the connection, exactly one way of defining the connection that has these two properties. Exactly one way. And that one way is known as the causal formula. And I derived it last time. It was kind of one of these miraculous things. And it's, I don't know if, I don't have the causal formula written down right now. But basically it goes like this. I don't know if someone can Google it and tell me what it says, but I don't know. It's probably not going to be possible. That's fine. Its notation is kind of annoying. But basically it gives you a formula. And you may remember there were 6 terms. We added them all up. And so it was going to be 1/2, and then 1/2 of 6 different terms. And
I have it if you want it.
do you have it? Tell me what form you have it. Go ahead. Is it this, or do I need to change the letters?
So I do it as 2g times that is all that.
Okay, thanks. Okay, good. So it's just x of y z plus y of x z minus, you guys like how I'm super well prepared? Z of x y and then minus the dot product of yx z minus x z y minus x z y minus y z x. Thank you very much. Awesome. You ever see a professor lecture off the student's laptop before? Okay, that's just like completely ridiculous, isn't it? Like, how can I come to class and not have the key formula ready to go, right? But there's a method to my madness. Let me defend myself after criticizing myself. I'm allowing you to see what's truly important. I don't have that formula memorized because I just look it up whenever I need it. Right? It's just some formula, right? But that is okay. I mean, now you can see that this is defined because if I know what its dot product with any z is, then I can figure out its component in every direction, right? And so that formula. Now, where does this formula come from? It comes from, I mean, Google it if you weren't here last time, but it's just use these identities 6 times, you add them up, and you can solve for that. Notice you can take the dot product of this equation with the vector field z on both sides. And then it's all about solving for these adding and subtracting. You plug into that formula, it turns out it works, right? You can see that these 3 formulas, right, are this identity here, right? Just plug in. In fact, maybe that's one way to see it is if you just take these 3 formulas here, right? The various permutations of x, y, and z, plug in here, you're going to get a bunch of terms like this, right? And then dot product this with z, and you'll see that this formula is just this thing here, and then do it different permutations. You're going to get a bunch of terms. It turns out all the terms cancel except 2 of these, and that's why the half is there, and then that equals that. Okay, so it's a very clever observation that these 2 identities actually determine what the formula is for the connection. Okay, and now I know what you're thinking. If you weren't here last time, you're thinking, oh, okay, but at some point you're going to tell me that this is all a formality. It doesn't really matter. No, it's not a formality. It does matter. That's what the covariant derivative is. And when you do computations in general relativity or any other form of, higher dimensional geometry, that's the formula you use. Yes?
So is this the definition of a connection? It satisfies those 2 properties?
Great question. Great question. Vocab is not my strong point. Okay, but let me try to get it right. A connection, this is the definition of the Levi-Civita connection. Okay? But mathematicians and physicists, we always like to play around with variations on a theme, right? And so very often this last condition is removed. And so this is called the torsion-free property, condition number 2. So if you ever there's someone who ever talks about a connection that has torsion, they're not talking about this connection anymore. They're talking about a connection that has property 1 but not property 2. And more generally, sometimes if you want to get really crazy, and I've done it, I've written one paper that did it. I didn't assume 1 or 2. I said, let there be some connection. Now, so that raises the question of what is a connection. And a connection is something that you take a vector field, you get 2 vector fields, right? And it's supposed to be giving you the derivative. So what is a connection? It's kind of funny that I never really said, right? I mean, I've suggested it's like a directional derivative of one vector field in the direction of another vector field. The main thing to understand is there's a unique connection that has these properties, okay? But implied in all this is that there are some properties that I didn't really emphasize. Is that, like, for example, we want if you multiply a vector field by a function, then we want to have this product rule here, right? Whoops, forgot my F there. Okay, so we want to have that multiplicative property there. We also want, if you have well, let me just stick with the first slot here. We also want that if you have 2 vector fields here, it needs to be linearly additive, right? Whoops. All right, and then in the x slot, we need to, if you multiply it by a function, that just factors out, right? And we need that if you have 2 vector fields there, then it's linearly additive. And these are properties that you had in multivariable calculus, right? So you take the properties you had in multivariable calculus and you say, okay, this stuff is like, obviously we're not willing to give that up, right? So this is a connection would be any, whenever you say obvious, then you realize, okay, wait a second, is that really obvious? It's just a definition. So mathematicians, we're not willing to negotiate on these properties here, right? So a connection is anything that satisfies those 4 properties, okay? And then if you want a metric compatible connection, it needs to satisfy property 1 here. And if you want it to be a torsion-free connection, it has to satisfy property 2. And then where everything becomes brilliant and wonderful is if you assume those four properties and properties 1 and 2, then there's only one connect. There's only one way to do it, right? So it's like if everyone talks about what is the connection. Well, I mean that's the connection, right? And everything else is a bunch of physicists trying to get fancy, right? And mathematicians too. But okay, but see, you understand? Like, is that really the connection? Because what if okay, let's. I would like to invoke ideas beyond science sometimes. Like, what if whoever, whatever created the universe, sometimes called God, right? What if God said, I don't care, I don't want the connection to be torsion free. You can't make me, right? Okay, well, I mean, I guess it could be, right? I mean, the point is, the universe I don't get to say what the laws of the universe are, right? So when we talk about the connection of the universe, I mean, maybe it's torsion free. Maybe it's not. How would I know? Right? Yes.
Is there some intuition for, what's your intuition for why that's called torsion? Like, I don't see the relationship between that and like twisting.
How about that? Before we go there, would you at least agree that this is reasonable to call this either the product rule or metric compatible? Right? So at least this one's well named, right?
Yeah.
1 out of 2 ain't bad. Torsion free. I think there is a reasonable answer to your question, but it's mostly historical. It's just a name.
Yeah.
Just keep in mind that, okay, how about this? If something is metric compatible, then with that, okay, I think it's probably along these lines. Y'all remember parallel transport?
Sure.
You take a curve and then you parallel translate a vector along that curve. Y'all remember that?
Yeah.
Right. So it's like, I'm walking and I say, okay, I'm pointing this direction, and I'm pointing in the same direction the whole time, and I walk around the surface of the Earth, right?
Yeah.
And it's just like, okay. If you have remember the definition involved the connection? It says that the covariant derivative of this vector field along the curve is 0.
Sure. Yeah.
Okay. A metric compatible connection will always make sure that the length of that vector never changes. Fair enough, right?
Yeah.
Because it's metric compatible. Right now, if it wasn't a metric compatible connection, you got some wild, crazy connection satisfies this, but doesn't even satisfy that. Well, then the vector could get longer or shorter, right?
Yeah.
Okay. What does this thing do? Well, when you don't have the second property, yeah, you still have that the length won't change, but that vector could do some spinning. It could spin around or something, right? But the length won't change.
Yeah.
So maybe it does some behavior or something, right? And so I think that's kind of where the imagery where it comes from. I don't think it's necessarily a great word name beyond that.
Okay.
It suggests some sort of twisting, right? But like as you parallel translate a vector, it can't get longer or shorter.
Yeah, because it satisfies a metric. So
Yeah, it's
length
compatible
is
with the metric, so it won't get longer, but it could twist or
have some
rotate
kind of
around.
Precession.
Yeah, it could be some precession or something, right? So I think that's the imagery of it. But then this, if you get rid of this, then it's saying nope, it's unique, and then by definition, what you're doing now, we're going to say that's not twisting. Okay, but if you get rid of it, then we'll say compared to this Levi-Civita connection, it's twisting. Make sense?
Yep.
Okay. All right. Now, let's just let me ask if there are any more questions, because actually I love when you guys ask questions. By the way, there's a book you can read if you want to get into this. It's by Barrett O'Neill. And it's called Semi-Riemannian Geometry. It's like 2 geometry books. I like the Semi-Riemannian Geometry book a lot. It's Semi-Riemannian Geometry with applications to relativity, which is why I like it. Okay? It's like my favorite geometry book because it understands that the most interesting application of geometry is general relativity. Or how about this? It at least recognizes you might want to do general relativity. Okay? In other words, you might want to have a minus sign in your rule of Pythagoras. A lot of books don't even do that. Like they just assume that all your metrics can't have minus signs. They always assume a positive definite metric. And that's cool and everything. It's just that it means I can't do physics, I can't do general relativity, right? So it's kind of lame actually, right? So semi-Riemannian geometry from the get-go does not make the assumption. It's kind of, this word semi-Riemannian is kind of silly when you think about it. Let me tell you the history of that. There was this guy named Gauss, and he was a super genius. And he came up with geometry and did a lot of cool number theory and statistics and physics, all kinds of cool stuff, right? But he technically sort of started what the subject of geometry is, and we learned about the Gauss curvature and the Gauss-Bonnet formula, right? Okay, yay for Gauss. He had a student named Riemann who was possibly smarter than Gauss. I don't know. Like, how can you have two geniuses like who knew each other? Like, it doesn't seem statistically possible, does it? Right? Or maybe we're just being too impressed by them. Maybe neither of them were that smart. I don't know. But Riemann was just incredibly impressive as well, and he took this subject of geometry and went with it. And so, talking about higher dimensions and recognizing that your surface doesn't have to be in a larger dimensional space, right? And just saying, let's start with this GIJ. In many ways, what I've been talking about today is Riemann, right? So Riemann's like, okay, let's just talk about an arbitrary metric. It doesn't need to. Let's talk about just intrinsic geometry without the three-dimensional space. And now he made one assumption though, and that is, let me tell you the assumption that Riemann made. So this is a Riemannian metric. What he did was assume that G, your metric, right? So G of, take any vector field, which by the way we can write as x dot x, whatever, however you want to. It's the same, we call it the same thing, but that's greater than or equal to 0 for all possible x. All vector field x, okay? And by the way, only equals 0 if x is the 0 vector. And that's a familiar property, right? Because a vector dot product itself should be the length of the vector squared. We can't blame Riemann too badly for that, right? But maybe he's not such a super genius that he thought he was. No, I'm joking. He didn't. I don't know if he was arrogant. Because that's not true in a space-time. That's saying you can't have a minus sign in your rule of Pythagoras. That's like, arguably, that's one of the most interesting applications of geometry is when you put a minus sign in the rule of Pythagoras and you start doing space-time geometry. You get the Big Bang and black holes and all that stuff, right? So he missed that. Riemann's like, oh, okay, I'm only going to consider this. Like, because obviously, otherwise it's stupid, right? Now, anything that is a subset of R3 or Rn will have this property, right? Because we know that. Because you're a subset of a Euclidean space where this property is true. And so the step he said is, look, I don't need to. I think, how was Riemann thinking? Maybe he was thinking of surfaces in R3, but he's like, look, I don't need to know the embedding. Let's just see what I can do without referring to R3. Maybe he was only thinking about geometries that came from being in some larger dimensional space, and is it possible that he didn't have quite the creativity to go beyond something that's not embeddable into a larger dimensional positive definite space? I don't know. I'm not a historian on this topic. But anyway, he assumed this. Okay? And so what is semi-Riemannian geometry? It's just when you don't assume that. Now does it mean like half or something? Does it mean half? Or does it mean partly? Partial? Okay. So what they're trying to say is, how about pseudo-Riemannian geometry might have been even better? I don't know. The point is, it's really Riemannian geometry. Okay, so just get rid of that assumption. Everything Riemann said was still true. So semi-Riemannian really is it's funny, I don't really like the term because some people, by the way, would just call it Lorentzian geometry. So I guess Lorentz was into putting minus signs in the rule of Pythagoras. So you could call it Lorentzian geometry. But then it seems like it's not giving Riemann enough credit because all he did was put a minus sign in there. All he did was remove one of Riemann's assumptions. By the way, Riemann also did great stuff in number theory. And probably the most famous open problem in mathematics today is called the Riemann hypothesis. It's about the distribution of prime numbers, but equivalently about the zeros of the Riemann zeta function in complex analysis. So that's pretty beautiful stuff. Like if a genie appeared and said you get to solve one, I'll let you solve one problem, right? What would it be? The Riemann hypothesis. It's on my short list. I'd have to give it serious thought, because there's some problems in general relativity I'd also be super tempted to want to solve. But the Riemann hypothesis is perhaps the most baffling. It's I don't know. It's a pretty cool question because it's about the distribution of prime numbers. I mean, doesn't that sound fundamental? It's really fundamental, right? So, yeah, I'd like to know more about the distribution of prime numbers. That's pretty cool.
What's the biggest like open problem in mathematical general relativity right
That's a really, really hard one. Like I could give you some answers, but then like something that will stand the test of time,
now? Yeah.
right? Anyone have a problem they want to nominate? I mean, I'll tell you the problem that I'm most actively trying to solve myself.
Okay.
It's called the Penrose conjecture. I mean, I already showed you all the Riemannian Penrose conjecture, which I did already solve. But what I didn't point out is what I haven't been able to do yet. It turns out the Penrose conjecture is saying the mass of a system is at least the mass contributed by the black holes, defined to be the square root of A over 16 pi, where A is the total area of the horizons of the black hole. What hasn't been done by me or anyone else is the case where you take an arbitrary slice of a spacetime, because the case that's been done, the so-called Riemannian Penrose conjecture, is sort of like a t equals 0 slice of a spacetime. But what if you take sort of a wavy slice of a spacetime? There's an analogous conjecture about the mass of that spacetime, the area of the area of the horizons of the black holes, and that's just the Penrose conjecture, and that's been open since 1973. And I'm kind of supposed to be working on that because I did the Riemannian Penrose conjecture, and so I'm sort of, everyone's kind of looking at me like, so how about the Penrose conjecture? And by the way, there's dozens of people around the world working on this, right? Everybody wants that, okay? Like, but I'm probably being a little biased to say that that's the most important problem. That's the problem that I would want to solve, right? Another important problem in general relativity that there's a whole group of people working on is the existence question, or the existence and regularity of solutions to the Einstein equation. Like, believe it or not, G equals pi t doesn't have an existence theory. Okay, which is a major shortcoming of the theory. Like, how can you write down the equation and not have an existence theory? And you take 353 or 356, they talk about these existence and regularity theorems for ODEs, right? They have existence theorems. Assuming this, then there exists a solution. We don't have that in general relativity, except in very special cases. So if you have data very close to Minkowski spacetime, like you start out almost exactly flat, then you get long time existence. Otherwise, nobody knows anything. Right? And, there's only some perturbations of some very special solutions where they know anything. Recently, people showed that if you have a perturbation of like a Schwarzschild or a Kerr, then you get long time existence. And everyone's like, oh my God, it's amazing. The paper's like 500 pages long and stuff like that. And it's like, this is not very satisfying. And I'll tell you where it gets even worse. I think they might be wasting their time. Because it's not even clear that's the right problem. I mean, general relativity is not the final theory of everything. Who cares if it has an existence theory? Do you get where I'm coming from? How about Newtonian physics? Does it have an existence theory? Who cares? Do you get my point? It's kind of, I mean, it's interesting, but you're talking about what's the most important problem, right? It's certainly not, does Newtonian physics have an existence theory? It's just a stupid theory anyway. It's not even right. Right? So who cares if it has an existence theory? By the way, it doesn't. It doesn't have an existence theory. I heard someone say this was the greatest mathematical thesis of all time. Someone proved that you could take 5 particles in a certain arrangement, and they're like two pairs spinning along an axis. Think of the z-axis, right? There's one particle moving up and down the z-axis, and then you got a pair of particles here and a pair of particles here, and they're spinning around the z-axis, and then they're coming in and then collapsing in such a way that you can get a configuration where it's not possible to solve the equations past that point. And now you might say, but what if you just have two? Like, how about 2 particles just coming right at each other, right? That seems like you're going to get, force of gravity is 1 over distance squared. So when they get infinitely close together, you're like, we're going to have a singularity, some sort of problem, right? But it turns out you can just sort of say they either bounce or pass through each other, and you sort of get if you want to, and there was some sort of weak sense, you could call that a solution, and say, okay, fine. We'll say technically you could solve through that. But this 5 particle thing that someone came up with as their PhD thesis, you can show that there is no weak solution where you can just solve through it or something like that. It's just Newtonian physics sometimes simply does not have answers. I mean, you can't solve for where the 5 particles are going to be at any point in the future because the equations can't be solved. This is where then there's a plot twist. If you really want to pursue this, is someone could say, oh, okay, yeah, sure, you can take 5 particles and they create a really weird situation where you can't solve fast it. But that was a very specialized situation you came up with, all right? And the odds of the universe having the 5 particles in that configuration is 0 anyway, right? So what if the set of, so could you just show that for practically all initial conditions, Newtonian physics has an existence theory, right? Well, that problem's still open. And then the same question goes for general relativity. By the way, in general relativity, there exists initial data where you can not solve past a certain point as well. Okay? And that's called the singularities inside black holes. So if you have a black hole collapse, turns out you cannot solve the equations past the singularity of let's say, even a short-shelled black hole. But then you're like, okay, so then the conjecture for general relativity is, oh, but that's fine. That's why we have black holes, right? Who cares what happens in a black hole? You can't see in there anyway, right? So the question is, outside black holes, maybe, you always can solve the equations forward in time, right? And that would be good enough because it doesn't contradict our observations because everything we see is outside a black hole. But then they came up with special solutions where you do have singularities outside black holes. And then we go back to the current conjecture is, okay, fine, you can have singularities outside black holes, but again, it's very specialized initial data, and the odds of that actually happening in any given initial data is infinitely small. It's like does that make any sense? It's sort of like if I say pick a random number between 0 and 1, the odds of getting exactly 0.5 is 0%, right? Infinitesimally small. But if you did, then that would cause a problem, right? So you just say that the set of bad data that causes singularities should have measure 0 in some sense in the set of possible initial data. So that's where they are in terms of existence theory for general relativity. I could talk about this for a long time. Let me just say that this is my own interpretation of this, is that I don't spend I'm not a PDE guy anyway. I admire and respect what those PDE guys are doing. It's so hard, so impressive, and they're advancing mathematics, so I salute them. However, the fact that general relativity does not have a very satisfying existence theory, the fact that it is so incredibly hard to even show you good existence theory in certain scenarios, to me, I think is giving you a hint that something wrong with general relativity. It's not the right theory. So, and we already know it's not the right theory. It doesn't do quantum mechanics. And of course, existence and regularity, it all comes down to regularity on a very small scale. And we already know that that's a quantum scale. It's a very, very small scale. It's quantum mechanics anyway. We already know the theory is not right on that scale. So trying to figure out existence and regularity for general relativity, I think it's ultimately going to be viewed, how's that any better than doing it for Newtonian physics? Right? And so really, what's the biggest open problem in general relativity? Well, I guess what I'm coming around to is trying to figure out what general relativity it really is. Like, what is the actual theory of the universe is the real question. That's, who asked the question, the biggest open problem? Was it you? Okay. Yeah, I mean, it's probably, I'd say something like along the lines of general relativity is not the final theory, so what is the final theory? Is there a final theory? How do we incorporate quantum mechanics into general relativity? That seems pretty important. And as a final thought, I think the correct final theory, if you're trying to ever put another physicist in the room, don't ignore existence theory. So come up with a theory that has an existence and regularity of solutions. At least existence. Why? Because I think, therefore I am. Like, what is that? Okay, that's a little bit silly. What is I think, therefore I am? What does that even mean? But how about this? Where I think I'll agree with Descartes is one of the most fundamental observations about the universe. It isn't the universality of the speed of light. Something even more fundamental than that. Can anyone tell me something more fundamental than the universality of the speed of light?
The universe exists.
There you go. I can't think of anything more fundamental than that. So if you come up with your clever theory, and it doesn't even have an existence theory, I can't take you too seriously. Right? That's got to be high up on the list of, there's got to be an existence theory. Okay. Other questions? Yes.
Yeah. Do you have any, like, why does the example of the 5 particles not have a solution?
I think what it roughly does is it manages to get one of the particles to accelerate to speed at infinity in finite time in such a way that they transfer like an infinite amount of energy to that particle somehow, and it's going super fast, and so you somehow you can prove that it has to continue to go infinitely fast, and so it can't be a finite solution. Something along those lines. I'm not an expert on it, but it's something along those lines. It's probably more subtle than what I said, but apparently it has a proof that there is no way to extend the solution. And you know, assuming something, you know, whatever they decide is a reasonable set of rules. I suppose if you wanted to get around it, you could try to redefine what they call a reasonable set of rules. You could always change Newtonian physics and say, when the acceleration gets to a certain point, then you don't accelerate that fast anymore. Things like this. You know, you can always try to modify it, try to come up with a theory that does have an existence theory. So yeah, these games go on forever and ever. Other questions, comments? Okay, so fun discussion. Getting back to what we've done here. So we have this arbitrary metric, which was our EF and Gs. Now we call it the GIJs. And by the way, just to be clear, you know, when I say the GIJs, this is, you know, in the case of a surface, it'd be G11, G12, G21, G22, and since the dot product is symmetric, then we want these two things here to be equal. All right. And by the way, for a surface, this is just the E, F, and G's. Okay, so the E, F, and G's literally are just the GIJs in dimension 2. Okay? And the thing that's different, though, is we have this connection. And so you say, you know, so how do I take the covariant derivative of a vector field in terms of another vector field? Let me show you how I do that, okay? Let me get a little bit more explicit about it. And that is that, well, what if, you guys remember how we can express vector fields as a summation of ij's and k's? You see what I just did there? That's an x upper I and a partial I. And summation over I is implied. Okay? And this is the same thing as saying if I had a vector field x and it equaled 3, 4, 5, right? I could say this equals 3 times I plus 4 times j plus 5 times k, right? Mm-hmm. Or in other words, it's 3 times partial 1 plus 4 times partial 2 plus 5 times partial 3, okay? But instead what we're going to do is we're going to write this as x upper I partial I. The summation over I is implied. I goes from 1 to 3. Do you guys understand?
Sure.
Okay. Notation is half of the difficulty of the subject, so I just want to dwell on that. Okay. Now, we can do the same thing for y. We can call this yj partial j. Now you might wonder, why am I using a j here instead of an I there? Well, it's because I don't. This i's and j's are dummy variables, but the point is there's two different summations going on. You're summing over I and you're summing over j. So this is, if we're in dimension n, this is n squared terms. Yes?
So do we generally assume, so x superscript I, do we assume that's a real number? Do we assume that's a field element?
It's a number at each point, which is otherwise known as a function.
Yeah, okay. But yeah, it's not necessarily
A constant.
Yeah.
Right. It does, like I gave the constant example because it's easiest for an example. What if instead it was 3 to the x, comma 4 to the y, comma 5 to the z, right?
Yeah. So
Yeah.
it's a function from our surface.
It's a function on the surface.
Function of a surface
To the real numbers. To the real numbers.
To the real numbers.
Generally, I mean, I like to keep the real numbers. Sometimes people can talk about complex value,
Yeah.
everything. But but then you're like, well, you can do that. But
Yeah.
Let's not.
Okay.
Let's not. Let's keep everything real. Okay. And then you can use, remember there's these properties of the connection? And so if you do that, then you can say, this is equal to, the xi just factors out, first of all, we agree? And then it's this. Okay, that was this rule right here, right? For connections.
Mm-hmm.
And then and now we got to do the product rule. And now we're going to do this rule right here, right? And so this is xi times partial I of yj times partial j plus yj times the covariant derivative in the partial I direction of partial j. Okay? Now, directional derivatives, the ant understands that. But this is the thing we don't have. What is that? Okay? So, in general, when you're taking these covariant derivatives, what it all comes down to is if you knew this for all I and all j, you'd be home free. Okay? And then you just do all your computations. And so what I've shown here is that all you actually need to know is a formula for the covariant derivative in the direction of partial I of partial j. You just need to know a formula for that. And then you can plug it in. You have a formula for the covariant derivative of any vector field in the direction of any other vector field. And I know the computations are it's like messy and long, and you're like, really? I mean, this is what you're doing all the time. Yes, this is computations in differential geometry take forever, and they're long and they're messy and they're complicated, and you got summations all over the place. But I just want to point out that complexity is actually theoretically easy. It's just computationally long and difficult. And for the physics majors in the room, maybe you know what I'm talking about. Sometimes computations get really long, right? And building up a tolerance for long computations, like, you know, it's like doing, if someone gave you a bunch of 2-digit by 2-digit multiplications, 34 times 56, and they said, okay, here's 1,000 of them, do them. Right? Well, I could do it. I don't want to do it, but I could do it. This is the kind of thing we're doing here, right? Just gotta be patient, okay? Yes, the equations get very long, but if you understand the ideas here, right? It's no more complicated than that. It just takes forever. Okay, so now what is the formula for this? Well, guess what? I don't have a formula for this. But I do have a formula for this because I can use the causal formula up there. And if I have this, then I can solve for that. Do you guys get the point? Okay, so actually, no. Wait a second. Yeah. So then, sorry. And so let's just call this gamma ijk. And there's a formula for this. And if you want to know what the answer is, we just plug in here. Now here's the cool thing, right? See how this has 6 terms? Turns out 3 of them are 0. 3 of them are 0. Can anyone tell me which 3 terms are 0 when I plug in these partial derivative vector fields?
The one I equals j.
Well, let's say I and j don't have to be equal, yeah, but it turns out 3 of these terms are 0 if you plug in these vector fields, partial I, partial j, partial k.
The ones that you take the dot product of the di and dj for the first 3.
Nope. That was a good guess. Someone says the second 3. Yes, the second 3. But why the second 3? You had to have a chance. You took a shot. If you were playing for money, that was the right move. Now, why the second 3? Partial derivatives have 0 lead bracket.
Yeah, because they're the course.
Yeah. So, because partial derivatives commute, right? Okay, so these are very special vector fields here. So yeah, these 3 terms here are all 0. And so what you're left with is that up there, right? And so what you get then is this is going to be 1/2. And now, what are these terms? Well, you take, this is x, y, and z, right? So when you put them in partial j, partial k, by the way, that gives me gjk, right? gjk. And then what I do is I take the derivative in the x direction. X is equal to partial I, so I need to take the I partial derivative of this. Okay? Now, do you guys mind if when I just put comma I there, and that comma I means take the I partial derivative? Now, I could have written, partial derivative with the round d and everything, right? But the comma I means take the partial derivative. Okay? So gjk comma I is equal to d dxi, right, of gjk. Okay? And sometimes you can just write that as partial I of gjk. All right, and so then you get plus, the second term is, let's see, gik comma j, and then you get a minus gij comma k. Wait a second. X, Y, yeah. Gij comma k? Yeah. I, j comma k. And there you go. Okay, so now, and by the way, if you're like, well, wouldn't it be more convenient if we actually solve for this? Like, this, what we actually want is, whoops. What I really want are these numbers here. I, j, k, partial k. So vector field, take the derivative of vector field in the direction of another vector field. That should equal a vector field. Any vector field is a linear combination of real numbers times the basis vector fields, right? And so we're summing on k here, and obviously it depends on I and j. So these coefficients are called the gamma ijk's. These are gamma ijk's, but the k is lowered. And there's a formula for what the gamma ijk is, where you have a raised index, and it so happens it equals 1/2 gkm, and then you do, this is something I do have memorized. Because I actually do use that all the time. So the formula I actually have memorized are these last two right here. If you take the covariant derivative of a coordinate vector field in the direction of another coordinate vector field, it's a linear combination of the coordinate vector fields where those coefficients are given by that formula right there.
What is M?
M is just another dummy index. You're summing over M.
Okay.
So notice, see M is raised and lowered.
All right.
So yeah, does this even make sense? By the way, you're summing over M. Okay, let's just be very clear. Over here, you're summing over K, right? But then to get this, you have to sum over M, because you have one raised, one lowered. So there's a summation over M here. So this looks like 3 terms, but actually it's N times 3 terms, because there's a summation over M. This looks like 1 term, but you're summing over K, so that's actually N terms. And you can see why the Einstein summation notation is useful, because I don't have to write down the summation signs all the time. So everything below this line right here is what I actually have memorized. And I don't need this Causyl formula anymore now. I just use the Causyl formula to compute this. And this is, I guess, look, it's complicated, but it's not that, it's quite as bad as that, right? So it's a little bit preferable. Okay. Slightly. I mean, you know, in mathematics, you guys in physics too, you'll be faced with a question, which is, should I do something the simplest way or should I do something the dumbest way? Should I do it the most clever way, where it takes the shortest number of equations, or should I do something just the dumb way, but it takes 5 times as many pages to do it, right? And the answer is both have value. Both have value. You want to be able to compute things in a clever way and also just turn the crank and get the answer. So actually, turning the crank and getting the answer, like, there's nothing wrong with that. As long as you get the answer. You guys understand my point? Nothing wrong. You don't need to be clever. So it's nice to know all these different formulas. It gives you different avenues of attack to try to figure things out. Questions before I move on? Yes?
So what you do is you take a metric and plug it in and see what the covariant derivative is, or you are looking for what kind of metric would satisfy a certain covariant derivative.
Typically, I mean, it's kind of a both, okay? But let's just say, for example, if I give you the GIJs, if I say, here's a space-time, I write down a metric. Like, for example, Minkowski space-time. Minkowski space-time, the GIJs are all zeros, except G00, time is the 0th dimension. G00 is -1, G11, G22, G33 are all +1. And so when you plug into this, you'll see, oh, all the GIJs are constants, so this is all 0, so all the gamma ij's are 0. And then it's saying that the covariant derivative of a partial derivative in the direction of another partial derivative is always 0. So in the case of if you have any constant metric, if the GIJs are any fixed constants and don't vary from point to point, then the covariant derivatives are all 0. Which makes sense, doesn't it? It's like a constant metric. Nothing is shifting around. But more generally, it gives you a formula. Other questions? I actually prefer to answer y'all's questions than anything else, because it slows things down, right, to the correct pace, the ideal, perfect pace. You actually ask great questions. Yes?
So there are 3 indices for the Christopher symbol, and then does M also vary with like the number of spatial dimensions?
Yeah, M goes, it sums over all the dimensions. So typically 1 to n. In the case of general relativity, it's 0 to 3. Yep. Other questions? Okay, so let's see here. I'm going to tell you what curvature is now, I think. But let's see here. I think I can erase the middle board here. So now we know what the metric is given. Now you might say, okay, what's an example of a metric? Maybe we should do that real quick because I mean the Minkowski metric is an example that's kind of maybe a little bit simple. Here's an example metric. I'm going to do a space-time because space-times are awesome. How about, I'll write it as minus dt squared plus a of t squared times dx squared plus dy squared plus dz squared. Whoops. And so to really put it into our note, and so what does this represent, by the way? This represents the Big Bang, typically. You have your a of t graph is a function of t. And your Big Bang starts out when that factor is 0. And here we are at 13.8 or so billion. Let's just do t in years. And then we'll do, yeah. So at 13.8 billion years since the Big Bang, that's where we are now approximately. Is that still the current number? What's that? What's that?
It hasn't been 100 million years yet. The 8.8's not changed.
That's right. Well, they're always estimates. I've heard every once in a while it might go to 13.7 or something like that. You know, it's like estimates change, right? They get more data and stuff. There's plus or minuses on these things, right?
Yeah.
But yeah, no, it hasn't. Approximately, you might know, around the nearest 100 million, right, years. And so that would just seem to describe our universe to some approximation. Okay, that's our universe. Okay, which is pretty amazing. I just write that down, and it actually works incredibly well. I mean, now here's the thing. This is on average. You guys know that matter curves space-time, so actually the space-time is bumpy, right? And this thing is not bumpy enough to get the nuances, right? But to some good approximation, this gets the overall shape of the universe. Now, how do we write this in this format? Well, what we have to do is, what we're going to do is, we'll call t, we'll call that x0, okay? And then x here will be x1, and then y will be x2, and then z here will be x3. You guys get the idea? And so then what we're going to do is we're going to say our GIJs. Now, I'll still use I and j, but by the way, if you ever do a relativity textbook, they always let i's and j's go from 1 to 3, and then alphas and betas, Greek letters, go from 0 to 3, okay? So I realize they've got some weird conventions like that. I'm going to ignore that convention for today, okay? Just so I don't have to use alphas and betas. I'll use i's and j's because we've been doing that. Okay, so GIJ then is equal to, now keep in mind, we're going to go from 0 to 3, so I'm going to get a 4 by 4 thing here. Okay, and so this is going to be, G00, and then we're going to get G11, G22, and so forth. You guys get the idea? Rows and columns, right?
Yeah.
G01, so forth, right? And so in this case, what these equal is we get a -1 here and then zeros. And then we get an a of t squared here, an a of t squared here, an a of t squared here, and then zeros. Okay, you guys get the idea? So that's our GIJs. There are 16 of them, but it's symmetric, so actually there's only 10 independent ones, right? And so G02 is actually 0, and so on, right? And then from that, you could compute your gamma I, j, k's equal, a bit complicated, isn't it? And I don't remember, but you can compute it using these formulas, okay? And you're going to have to say, well, if I and j, you really have to split up into like, I don't know, a bunch of different cases. You got to compute gamma 0, 0, 0 will be one, then gamma 0, I, j, gamma, or 0, 0, I. And then you're going to start to understand why you use Greek letters if you want them to go from 0 to 3, and then Latin letters, I, j, and k, if they want to go from 1 to 3. But anyway, you got to compute all the different possibilities, right? And it's slightly annoying. All right, yeah, it's slightly annoying. All right? I mean, it's like to compute stuff like that. It's going to take you an hour, 2, okay, just to compute what the Christoffel symbols are. These are known as Christoffel symbols. Okay, Christoffel symbols. Everybody gets their name in on this. Symbols. You got the, okay, let's remember the names. The causal formula was the thing I erased. It's defined to be the Levi-Cheat connection if it satisfies those two rules. And the coefficients are called the Christoffel symbols. They must have been friends. They were like, I tell you what, I'll take the names of the symbols, you take the name of the formula. I don't know. Okay. All right. And so now, what is the point of all of this? Well, where did this come from? Like, you know, who? You're like, wait a second. You're telling me? In other words, this actually comes from G equals 8 pi t. G equals 8 pi t, and then you set it equal to the matter that you see, matter observed in the universe. All right. So you set it equal to the matter observed. That tells you that the t roughly, and then as you solve for the g, you get this. Okay, and it predicts a Big Bang. Yes.
What's an example of a space that has a metric that isn't diagonal?
The simplest example that comes to mind is a rotating black hole, which is called the Kerr spacetime. If you have the Schwarzschild spacetime, I've shown you before, that one's diagonal, isn't it? But when you rotate it, then you're breaking a symmetry. You're breaking the spherical symmetry. So the Kerr spacetime, you Google it. Kerr, I think, is still living. He's an old man. And this guy, pretty impressive. Just Google Kerr spacetime if you have a computer right now and see how complicated it is. And he solved G equal 8 pi t equals 0 for a black hole that's rotating and came up with that metric in 1950 something. Right? And I have to say, how the hell did you do that? Here it is like 70 years later, and I'm still like, how did you do that? I guess it's just persistence, mind over matter. I have no idea how he did that. I mean, it seems, by the way, maybe it's not as hard as it seems, but it's a pretty complicated metric. And the Schwarzschild spacetime is an exercise, and I understand how you do that. But it's, well done, is all I can say. Well done to Kerr. Solving for the explicit solution of a rotating black hole. I mean, who's to say that would even be possible to write it down explicitly? So now, what have we not done? In the last 5 minutes, tell you what we can do next time. Is I haven't shown you what this Einstein curvature is. What's this curvature, right? What's that, right? So how do you solve? So someone asked, like, if you're given the metric, you can compute the connection. And by the way, with the connection, then you can compute its curvature. And then you can set it equal to the matter density observed, and you can get this. All right, that's the game we're going to be playing. But what is curvature exactly? We don't know yet, do we? Like we've heard that we did the Gauss curvature. That's a formula in terms of the EF and G's, right? And so it turns out that this curvature is going to equal some function of the EF and G's. Not surprisingly, right? Except we don't have EF and G's anymore. We have GIJs, right? And so it's going to be a function of the GIJs, but also not just the GIJs, but also the GIJs, and then take one derivative, a partial derivative. I'll put a semicolon here, right? And then take the GIJs. Remember, there were actually second derivatives of the EF and G's. You all remember that? 2 partial derivatives in terms of U and V. So actually, it's going to have up to second derivatives of the GIJs in there. And there's going to be some rather complicated function. And I wish I could tell you that all of a sudden everything gets really simple, but come on. You saw how complicated the formula was for the Gauss curvature. That was dimension 2 with a positive definite metric. Okay? It's going to be, even more complicated than that. All right, but not outside of range. We're going to be able to write the formula down, and we're going to be thankful that you can do that. We're going to be like, oh, look, I can write down the formula for curvature. It only takes me a weekend to do computations, right? And it's like, okay, fine, I got a weekend. And so that's what we'll do next time, is figure out what curvature is, and then when you set equal to the matter density observed in the universe, then you can find the shape of the universe and so forth. And this A of t is actually something that you can solve for. And it's also something you can measure. You can look through telescopes, and you can literally see how big the universe is compared to other, more or less. Now, what can you actually see? They observed the A of t. By the way, a Nobel Prize was awarded for observing the A of t. Okay? I think it was like the 2011 Nobel Prize in Physics, something like that. And what they did is they looked through telescopes and they saw all these type 1A supernova explosions. Okay? And what's nice about type 1A supernova explosions is that they always have exactly the same intrinsic brightness. Okay, the size of the explosion is always the same. Which means that you know how far away they are based on how bright they seem to you, right? Because they're all inherently the same brightness. So now you have a distance away. Guess what? Light travels at the speed of light, which means you know when those explosions happened. In other words, you're looking back in time. So if you see something and it's really dim, you're like, oh, that's dim like it's 8 billion light years away. Oh, that happened 8 billion light years ago. So you're literally looking at something that happened over here, right? And guess what? You can look at the color of the light and see how redshifted it is. And that tells you how rapidly the supernova is moving away from you. And that tells you that gives you some measure of the expansion of the universe, which is the rate of change of this AFT. And so essentially, when you're looking back, so you have 2 bits of data, when it happened and how fast it's moving away. Well, guess what? 2 coordinates here, right? 2 bits of data, right? You can take that and then put the dots. In each supernova explosion is a dot, and then you can put the curve through the dots, basically, roughly, to oversimplify, possibly lie just a little bit. Okay? But roughly speaking. So you can measure this AFT curve, but then you can also look at the matter density of the universe, plug it in there, and solve for the AFT. They agree. Right? Which is pretty cool. By the way, they agree as long as you put some dark energy in there. If you don't put dark energy in there, they don't agree. And so that was why one of the reasons they got a Nobel Prize was that what they noticed was that, you see how since this point right here, about 10 billion years after the Big Bang, you see how the curve is actually curving up a little bit? It's not curving down anymore, it's curving up. That is not something that can be explained without, so the simplest explanation known is saying, oh, well, maybe there's some dark energy in the universe. And you say, well, what is dark energy? Well, it's just a term that Einstein played around with a long time ago. It's a very natural term. I think I might have mentioned it on the first week of classes, did I? Perhaps. But you might call it a cosmic fudge factor, right? If you want to be sort of critical about it and say, does dark energy, it's not to be confused with dark matter, by the way. Dark matter is most of the massive galaxies, which is fascinating in and of itself. I mean, dark energy is most of the mass of the universe. So it turns out that to get general relativity to work, you have to assume that most of the mass of the universe, current day, is invisible and is unobserved except for the fact that it causes this curve to curve up at the end. Right? So then it kind of raises the question, wait a second, is this true or is this just a giant fudge factor to make your theory work, right? And then you're like, oh, okay, well, how about on the scale of galaxies? Surely general relativity works on the scale of galaxies, right? Nope, not unless you put in a bunch of invisible stuff we call dark matter, and then it works. Yeah, as long as you can just put matter wherever you want, and say, yeah, it's there, and that's why you see gravity, then your theory of gravity works. That sounds pretty hokey, doesn't it? So dark matter, but on the other hand, it actually works pretty well, and I think the smart money is on that dark matter is really a thing, actually. I think that's the smart money, but that's just the current best thinking today, okay? So, because I mean, why is it that you should be able to touch and feel and see matter, right? Just because you can touch and feel touch, see, and feel real matter. Well, some matter doesn't mean you can touch and see all matter, right? I mean, right? But then you go onto the scale of the solar system, and guess what? General relativity doesn't need any fudge factors, doesn't need any dark matter or dark energy. It works perfectly. All right? So that's the current state of affairs. It's actually a pretty amazing story. And we'll figure out how to do curvature next time. And it'll generalize our notion of Gauss curvature. All right. Y'all want to say?